This video is on Newton's law of gravitation and gravitational field strength. Question 1. State the names and describe the laws of Kepler's three laws of orbital motion. So the first law is the law of orbits. A planet travels in an elliptical path, and the sun is located at one of the two foci. So if you don't know what these mean, go online and find out the meaning of ellipse. It's like an egg shape. Understand the meaning of a foci. It's one of the 2 points in an ellipse. The second law of Kepler's orbital motion laws, it's the law of equal areas. A planet sweeps through equal areas during equal time, since the planet travels faster when it is closer to the star. So in the same time, looking at this image, S1 has the same area as S2. And finally, the law of periods. Period squared is proportional to radius cubed, where t is the period of the planet and r is the length of the semi-major axis. So think of it this way. Look at this image on the bottom left. You have the planet going really fast as it gets close to the sun. Then the sun pulls the planet. Then the planet goes slower as it goes away from the sun. But it slows down because the sun is still pulling it. Here at the very right, the sun pulls the planet and it speeds up. And then it passes the star, the sun, because of its inertia. And then it continues to go fast, but changes direction. And then it slows down. So think about inertia. You know, that's why it goes past the sun, because it continues to go forward. Question 2. Define Newton's law of gravitation. F sub g equals m1g equals g m1 m2 over r squared. What are the units? So in physics terms, Newton's law of gravitation tells us that the force of gravity acting between 2 point masses are proportional to the product of their masses and inversely proportional to the square of their separation. So you could take a look at this equation and understand what that means. So the more mass an object has, the more attracted it is to the other object. And the closer the two masses are to each other, the more the two objects are attracted to each other. So Newton's law of gravitation tells us that the force of gravity between at least, it tells us the force of gravity between at least two objects with mass. A minimum of 2 objects are required for this equation to be used. There can be more than 2 masses used to determine the force of gravity. The force of gravity, unlike the electric force, is always an attractive force. And treat m1 and m2 as point masses. So big G is the gravitational constant, 6.67 times 10 to the minus 11. We'll see examples of this equation in use at the end of this video, hopefully. Question 3. A satellite in space moves in a counterclockwise circle around the Earth with a constant speed at a radius r from the center of the Earth. Label the direction of the velocity, force, and acceleration of the satellite in the diagram below. So remember, sigma f equals ma, so sigma f and a always point in the same direction. So f and a is towards the planet, the center of the planet, and the velocity is 90 degrees. So f and a. Question 4. The force of gravity between a satellite circling the Earth at a distance r at a constant speed is force of gravity, F sub g. What will happen to the magnitude of the force of gravity between the satellite and the Earth if the satellite moves a distance 2r? So now the satellite is a distance 2r from Earth, not r. So F old, we have gmm over r squared. F new, r becomes 2r. So now we get a 1 over 4 in the denominator. We get a 1 over 4 in the, as a fraction. So now the force of gravity is only 1/4 the original force. Imagine if a satellite goes from a distance r from the center of the Earth to 3r. What happens to the new force of gravity? Well, you put 3r in the denominator, that becomes 3r squared once you square it. So you get this 1/9 hanging out. And what if the distance of the satellite to Earth is a distance r from the center of the Earth to a distance 4r? Well, r in the denominator becomes 4r. You square 4r, you get 16r squared. Now, what happens if the satellite goes from a radius r from the center of the Earth to a radius r over 2? So r over 2 becomes r squared over 4 if you square it. The 4 goes in the numerator. So if you decrease the distance of a satellite to the center of the Earth, then the force of gravity increases, as you can see. Question 5. A satellite is moving in a circle with a constant speed around the sun. Use Newton's second law of motion to obtain an equation for the speed of the satellite in terms of the mass of the sun, m sub sun, the mass of the satellite, m sub satellite, the distance of the satellite to the sun, r, and the gravitational constant, g. So let's determine an equation for the speed using Newton's second law of motion. So because it says Newton's second law of motion, just write sigma f equals ma. The force between the satellite and the sun is gmm over r squared. That's equal to mass of the satellite times acceleration of the satellite. Acceleration of the satellite is v squared over r. Solve for v satellite. You get what's in yellow. Now, now let's take a look at part B. Use your solution to obtain an equation for the period of the satellite. Speed is distance over time. So the distance of the satellite around the sun, if it's going to go in a circle, is 2 pi r over t. T is equal to 2 pi r over v satellite. Here we're going to substitute what's in yellow here in the denominator. And now we're going to square both sides because we don't like r to the 3/2. Now we have period squared is proportional to a constant times the radius cubed. This is Kepler's third law. So understand what I did here, because this is a very famous derivation to derive during an exam. Question 6. The mass of the sun is approximately 1.99 times 10 to the 30 kilograms. The Earth is approximately 1.5 times 10 to the 11 meters from the sun. Use this information to determine the speed of the Earth and the period of the Earth. So we're going to use this equation and this equation. The speed of the Earth is about 2.91 times 10 to the 4 meters per second. And the period of the Earth in days, we solved for it to be this in seconds squared. So take the square root of both sides, we have this in seconds. Now we're just going to multiply by 1 3 times. So seconds in the numerator cancels with seconds in the denominator. Same with minutes and hours. So we get about 375 days. This is close to 365.25 days. So what if these values are more accurate? The value of the mass of the sun, the value of the distance of the Earth from the sun. Question 7. A satellite which has a mass of 550 kilograms and a radius of 2.2 meters is orbiting the Earth at an altitude of 375 meters. A. What will be the magnitude of the gravitational force between the satellite and the Earth? So just use gmm over r squared. B. What must the velocity of the satellite be in order for the satellite to remain in a stable orbit? So we derived this equation maybe 2 problems ago. Part C, what will be the magnitude of the centripetal acceleration of the satellite? So remember, in circular motion, acceleration is v squared over r. Part D, how long in seconds will it take for the satellite to orbit the Earth once? So we have this equation for t squared. We solve for t squared. Take the square root of both sides to get t. Question 8. The following problem refers to gravitational field strength. A. Define gravitational field strength. Is it a scalar or a vector? The gravitational field strength is a measure of the gravitational field in a specific location. The gravitational field strength has a mass as a source and attracts other objects with mass. Gravitational field strength is a vector. Part B, what is the equation and what are the units for gravitational field strength? Define and give the units of each variable. So gravitational field strength is gm over r squared. Has the units here of newtons over kilograms. Or meters over second squared. Something you're very used to. Part C, where is a gravitational field strength 0? Where is a maximum? It's 0 at infinity, meaning when you're infinitely far from another object. It's maximum at the surface of an object or planet. Part D, what are the mathematical limits of gravitational field strength? Could it be positive, negative, 0? It's always between 0 and infinity. Question 9, the mass of the Earth is approximately this and its radius is approximately this. Use the equation g equals gm over r squared to determine the acceleration of gravity near the Earth's surface. So using this equation we get about 9.78, which is really close to 9.81. So what if the value of the mass of the Earth and the radius of the Earth are more accurate? We would be much closer to 9.81. Question 10. Draw a gravitational field strength versus distance graph for a planet with radius r. So when we're inside the planet, gravitational field strength increases linearly. When we're outside the planet, it decreases as 1 over r squared. Question 11. List some rules in drawing gravitational field lines. So these two images are gravitational field lines. Gravitational field lines tell us the direction an object will move when given at that point. So imagine like anywhere where there's an arrow, put an object on that arrow, and now release that object. The arrow tells you the direction in which that object moves. So you could see by looking at this top image, the blue object has more mass than the orange object. Because if you look between the blue and the orange, more lines go towards the blue. Now if you look at the second object, you have the Earth and the Moon. The gravitational field strength of the Earth is stronger than the gravitational field strength of the Moon, because you could see if you look in the middle between the Earth and the Moon, the Earth pulls objects to itself even if it's closer to the Moon. Let's read the second bullet. Gravitational field lines always point towards objects with mass, never away. The more mass an object has, the more gravitational field lines it will have. Gravitational field lines are always perpendicular to the surface of an object, and gravitational field lines never cross each other. So question 12, use a pencil and ruler, draw gravitational field lines for each figure. So the image on the top left is a fixed uniform spherical mass. The image on the top right are two uniform spherical masses with equal mass and equal radius. And finally, we have two fixed uniform spherical masses where M1 has a much greater mass than M2. So the blue lines are lines of gravitational field strength. So you could see in the first image, the lines are like straight lines that go towards the center of the object. In the second image, you could see the gravitational field lines, they always hit this planet or these two planets 90 degrees from the surface. I know my drawings are a bit terrible, I apologize. And the third image, you could see even if we're closer to M2, objects go towards M1 because M1 has more mass than M2. So the M1 has more of a pull. Question 13. The center of a planet of mass 4m is a distance 5d from the center of a larger planet of mass 9m. Assume that the mass of the planets can be concentrated as their centers. What would be the gravitational field strength at a point, part A, 2d to the left of mass m1? So mass m1 is on the left here, and if we're 2d to the left of mass m1, that means m1 pulls the object to the right and m2 pulls the object to the right. So you see we have these two positive signs because I'm letting the positive direction point towards the right. So m1 pulls this object gm over r squared to the right. Mass m2 also pulls it gm over r squared to the right. Okay. Now what if we're 2d to the right of mass m1? So here's m1 and we're going to be 2d to the right of mass m1. So part A was to the left, part B was to the right. So mass m1 is going to pull this object to the left. That's why we have a negative sign here. And mass m2 is going to pull this object to the right. So you have a positive sign here. If we're 2d to the right of mass m1, the object is 2d from m1 and 3d from m2. So that's why I have a 2d here and a 3d here. You do the math, you end up getting 0. So if we're 2d to the right of mass m1, the object will stay stationary. It will not move to the left or right. Part C, what if we place an object 2d to the left of mass m2? If we place an object 2d to the left of mass m2, mass m1 pulls it to the left and mass m2 pulls it to the right. So it will be 3d from the left of mass m1 and 2d to the right of mass m2. So that's why there's a minus sign here and a positive sign here. And there's a 3d in the denominator and a 2d in the denominator. Part D, what if we're 2d to the right of mass m2? If we're 2d to the right of mass m2, we're 7d from the right of mass m1 and 2d from the left of mass m2. And both of these masses pull this object to the left. So if positive x is to the right, sorry, we're looking at part D, we got negative signs. Question 14, Earth has a mass of approximately this, while Mars has a mass of approximately this. Both planets are separated by approximately this and can be taken to be point particles. How many meters from Mars does a 3,000 kilogram white rhino have to be placed to feel no force? So for this white rhino to not move at all, we need to use sigma f equals ma. A is 0. So the Earth pulls the rhino to the left and Mars pulls the rhino to the right. So that's why there's a negative sign here. That's why there's a positive sign here. And we just solve for x. Let's use our graphical display calculator. Question 15. A rock in space which is initially at rest has a mass of 400 kilograms and is 6 times 10 to the 3 kilometers away from two fixed rocks, each with a mass of 1 million kilograms as shown in the image below. What is the acceleration of m1 at the moment when it is released from rest? So you could see when you release the m1 from rest, m2 pulls m1 down to the left, m3 pulls m1 down to the right. And look at the symmetry. m1 is 6,000 kilometers away from m2 and m3. So it looks like the horizontal motion of m1 is going to be 0. m2 and m3 are just going to pull m1 down. Vertically down. So remember the rules for a free body diagram. Circle the object, label the forces, put an x and y axis, use the equation. So I circled m1, I labeled the forces, force of gravity 2 on 1, force of gravity 3 on object 1, I put an x and y axis, and now I'm going to use the equation. So due to symmetry, sigma f sub y is 0 newtons. Now make sure your calculator is in degrees. So sigma f sub x, it's going to be ma. So this, what I highlighted is mg here. So we know big G is a constant. We know the mass of our object is 400 kilograms. We know the mass of the other object on the bottom. We know the distance between the two. And we're multiplying it by 2 just because of symmetry. There's mass m1 and there's mass m2 and mass m3. So we're going to use trigonometry to find this relationship, cosine of 2.5 divided by 6. You can see that, right? Because this is a right triangle, becomes 2,500 kilometers. This becomes 6,000 kilometers. So this is sigma f. We know sigma f equals ma. We know what m is. So now we could solve for a.